group that we would hope to, time is it? Yes, it's time to start. I think some folks probably know about Weil groups and may not be here, but that's fine. So this is everything we would hope to find. For example, this would be I don't want to mess it up too much. This would be the mixed that would be the mixed exponential automorphic Galois group. This would be GF tilde plus. So we haven't talked about some of these things yet, but this is what it seems to me what would include everything we would hope someday to get. And I'll be perfectly happy if we can. I'm not going to be able to finish lecturing on it, but if we can, if perhaps it gets figured out in a month or two, what all of conjectures, reasonably precise conjectures as to what all of these would be. So this would be the mixed exponential motivic Galois group. This is all F global. And what else? This would be the mixed. I'll just do these ones. T tilde would be the mixed. No, it's not. It doesn't matter. It's not mixed. It's the Tanyama group, but the exponential Tanyama group. So we'll be talking about this later today, and so on. Okay. So the purpose of this lecture is to bring us up to speed for Weil groups. And the reason I put the diagram down was to illustrate that, I still hope I got the diagram right. There should be 1, 2, 3, 4, 5 rows, 5 columns, and 6 rows. Five columns and 6 rows. The reason I've written this down is not to be ostentatious, perhaps, or too unrealistically hopeful, but rather to just illustrate where what a part of things the Weil group is going to be. So WF would be some extended or exponential Weil group. WF would just be the Weil group. All right. Okay, so that's just to perhaps give ourselves a sense that the Weil group plays an important role in all of this, especially particularly on the automorphic side of things. It's a step above the Galois group, but a step below the automorphic Galois group. Okay, so Weil groups. I'll see how much I can do here. F is local or global for this discussion. Then there exists a canonical extension of locally compact groups. One, CE. We've talked about CE as if and I'll say so. Weil groups. F is local or global, and E over F is finite Galois extension. Okay, so there's then canonical extension that goes like this. The Galois group of E over F and 1. Where you remember in a local field, CE is the multiplicative group of the local field. And in general, it's the E-Dal class. For a global field, it's the E-Dal class group of E. And so it is given, so there's a local extension of groups given by a canonical element. Alpha, which something that gives extensions, namely H2 of the Galois group, finite Galois group, with coefficients in CE. You have one of these things, you have an extension. And this thing is called the fundamental class. Called the fundamental class, and it's at the center of class field theory. We talked a little bit about class field theory maybe a couple of weeks ago, or at the heart of class field theory. So why would that be related to class field theory? Well, in fact, the image theta, I'll call it theta of C theta alpha is so the image theta, I'll write it here, sorry, theta alpha, the image of alpha in H2 of gamma E over F in the quotient group of CE. In other words, so so the image of H2 in I'm going to write this down and then just say what the image of this is. So this is H2 of the Galois group, not in CE, but in the Galois group of E abelian over E. So I'm talking about the image of this in the group of connected components. Okay, CE is the E-Dal class group globally, and it has a connected component, which is rather interesting and disagreeable. but sometimes disagreeable. But in any case, this class here, this fundamental class, much of the proof of class field theory is trying to understand this class. And it's actually in here. This is a group that could have a connected component of 1. But if I were to take its image in the group of connected components, that's just the Galois group. It's a quotient of the Edel class group, and it's at just the Galois group for local field. And so my assertion here is this is the class that gives the extension 1 gamma E abelian over E gamma E abelian over F gamma E over F to 1 that's dual to the extension of fields. We've got 3 fields sitting around there. We've got the maximal abelian extension of E, we've got E, and we've got F. That's an extension of 3 fields. And so you've got the maximal abelian extension of E, you've got E, and you've got F. Okay, so class field theory gives you the maximal abelian extension of any number field or local field in a very striking way, a beautiful, just astonishingly, to at least at the time, like 100 years ago, a seemingly astonishing result. But then that's it. Class field theory studies this. But suppose E is a Galois extension over this. What would be the maximal abelian extension of this bigger field as an extension of F? And that was the question that Weil posed to himself, I think. Maybe, I don't know if people thought about it before, as to what that would be. And Weil just said, look, it's just given by the fundamental class, which is something that my history is not that good, but probably the fundamental class in one way or another was part of perhaps what people already knew. This was Weil in perhaps 1950, around there. So actually now it turns out, so this is going to be a fast lecture. Yes, Walid. Yes, class field theory tells you the maximal abelian extension of E, but there's something else. Once you got that, there's something else, and another sort of related question you can ask. What if E itself is a Galois extension of a smaller field? How do you write the relation of the smaller field, or how do you write the Galois group of the smaller field as a subfield of the maximal abelian extension of E? So there's something a little extra there that goes beyond class field theory. And they said, well, it's this fundamental class that we, this canonical thing that we study. And so that motivates why you like a Weil group. It turns out, so I'm just going to say, the article for this is Tate's number theoretic background in the Corvallis conference. It's a rather challenging article to read. He doesn't. He's got his own particular sort of very canonical way of doing things, but it turns out to be simpler. I'm just going to say, even though this may look counterproductive, it turns out to be simpler. To let E vary. So E in this, E could be some huge finite extension, Galois extension of F, and simply define the absolute Weil group to be the limit over E. F is fixed, but E over F is Galois of these Weil groups, Weil group of E over F. Absolute. Langlands doesn't do that, but Tate does. In other words, just start with this. And I'll say a word about that in a moment, but just what ends up happening in this situation, it's the absolute Weil group, is 1. So this can be local or global. F can be local or global. If F equals C star, the Galois group of the algebraic closure of F is itself, of course, just C star. And I'm sorry, that's not silly. The Galois group is 1, and the Weil group is equal to C star. So the absolute Weil group is very simple in that case. It's also, of course, you don't need, in that case, there's no finite extension, and the same is true of the reals. But if F is the reals, you don't need, the absolute Weil group is the same as the Weil group because it's algebraic closure is the Galois group C over R, which is Z mod 2Z. So you're talking about the absolute Weil group being actually a relative Weil group because you only got an extension of degree 2. And in this case, this was a very timely discovery by our observation of Langlands at the time. He used what I'm about to write down as a fundamental way of classifying the irreducible representations of a real group. But WR, what is it? It's an extension here. WR is the same as WC over R. And so it's just an extension of the multiplicative group of complex numbers by a group of order 2. And so in this case, WR is the group. So it's the same thing as WC over R. And it's the group. Aren't too many groups like that, but it's the group, it's an extension of degree of this of C star of order 2. So it's the group generated by C star. Okay, it contains C star as a subgroup of index 2, and then one element, an extra element, sigma. With relations, sigma Z, sigma to the -1 equals Z star, Z bar, no surprise there, but it is not the direct product of the two. It's the unique non-trivial extension. That is to say, sigma is not a generator of the Galois group of C over R, but rather an element whose square is not 1, but -1. So it's a non-trivial extension. One, C star, WR, non-trivial in the sense that it's not a semi-direct product. Z mod 2Z, that's the Galois group of R. 1. 3, these are local. If F is equal to QP, it's a little bit different here. It's a little bit of a surprise, perhaps. Then I'll just write it down as we've got an extension. We've got IF That's the multiplicative group of the field. No, I'm sorry, it's not. Sorry, hold that. The Galois group. And I'm going to write the Galois group for unramified. And below, I've got almost the same thing. I've got IF. But then here I've got the Weil group rather than the Galois group. And I've got here, I've got the subgroup of the Weil group or the Galois group generated by the Frobenius. So that's a cyclic, an infinite cyclic group. And so the point is that in this situation, the Weil group is not a quotient or something a little bit bigger than the Galois group. It's actually smaller. This is the inertia group. So a p-adic field is an extension of the cyclic group generated by the Frobenius by a subgroup. It's a non-trivial extension. It's a non-trivial extension, and that subgroup is called the inertia group. This is just the Frobenius element, which is something that this is Frobenius, exists in any p-adic field. And so the Weil group, this is a subgroup of this. The thing is that the Galois group is compact. It's a compact, totally disconnected group. This is compact. This is not compact. But it's almost the same as this, except instead of taking the compact group, the projective direct limit of quotients of the Frobenius, which would be a compact group with a cyclic topological generator, you just take this group itself. So this is a subgroup of this generated by an infinite cyclic group. The same phenomenon holds for this. It's just that you add the inertia group. So IE, I'll just say IE. In this case, WF is a subgroup. Of the Galois group with dense image. So it's kind of the opposite of what's happening for the reals. That's the Weil group is something bigger than the Galois group. It's an extension of the Galois group. But in both of these situations, what's really relevant, you're going to be, as we'll see when I write out Langlands questions 6 and 7, what is of interest in the classification of local representations is maps of the Weil group, the local Weil group, into the L group. And in both cases, the case that the Weil group is bigger, for the reals, for example, it's an extension of the Galois group, or here, this is where the Weil group is a subgroup of the Galois group, not an extension. It's a subgroup of the absolute Galois group, but nonetheless, because this has dense image, you're going to be requiring that these homomorphisms be continuous. Because this has dense image, it is the homomorphisms of the Weil group into the L group are going to be, there are going to be more of them if you take the Weil group rather than the Galois group, even though the Weil group is a subgroup of the Galois group. And the reason being that this has dense image in here. And so if it's continuous, then you're talking about a continuous homomorphism of this group into the L group, it's going to only be a finite image. If it's complex, if it's a totally disconnected group, the homomorphism of that group into something continuous is only going to have finite image, whereas this doesn't. It leaves you room to let Frobenius be anything you want. Okay, So that's what we're talking about for Weil groups. Well, I should just say, I won't try to say what happens to the Weil group for the global field. If F is global, those first three were if F is local. If F is global, I'll just say that Weil group is more complicated. What's actually interesting and relevant is, even though that what is often considered would be the group of connected components in the global Weil group, the connected component of one is also very interesting and plays a big role in some of these things. Okay, so this is all in Tate. Well, it's also in much of it's in Langlands without the absolute Weil group. This is Tate, number theoretic background. Corvallis. First article in volume 2 of Corvallis. And what he does is he does the opposite to what we've done here and what Langlands does. He starts with the absolute Weil group, VF, WF, and he starts by simply taking it to be a locally compact group. But was satisfying 4 axioms. He writes down 4 axioms for this locally compact group, which characterize it. So it's the opposite. And then he defines the relative Weil group. Okay, so the relative Weil group, WE over F, which is what we started with, as simply the quotient of the absolute Weil group. Now, it's not the absolute Weil group modulo the smaller absolute Weil group of the bigger field. If we've got a bigger field, the absolute Weil group is smaller. And it's not that, it's something smaller still. It's the absolute Weil group of E, but not just this thing, but rather its commutator quotient. The quotient of the Weil of WE modulo WE is reserved for something else. For any finite, all of this, it's implicit that E is a finite Galois extension. One doesn't have to make it Galois, but it illustrates what we're doing a little more clearly. For any finite Galois extension, E over F, the Weil group of F, modulo the Weil group of E. This is what would be the Weil group of E over F. If you take the quotient of the absolute Weil group by the whole absolute Weil group of E rather than its commutator quotient, what do you get? Well, there's something else that you get, which is, of course, very relevant, just the Galois group, something smaller than the relative Weil group, the Galois group. All right, So we're moving right along here. We might be able to finish. Yes. That's what I'm afraid I've got, yeah, yes. So that's a very quick run through of what Weil groups are. So the reason I'm doing this is partly because the Weil groups are a fundamental part of the larger story, and also to just clear up the last two questions in Langlands' original article. And those questions actually turned out to be a little bit murky. It was absolutely the right track of Langlands, but there were things that probably he had in mind, but he didn't describe explicitly in the conjectures. And so I'm going to just describe the last two questions, let's say in updated form, what they mean in present day understanding. So question 6. So last two questions. Okay, so question 6 is, so these are his last two questions updated. What they mean these days in the field for mathematicians. So question 6 is local, question 7 is global, as these questions have been pairing off. And question 6 is the local Langlands question. It's a conjecture, the local Langlands conjecture. And it's fundamentally tied to the Weil group. And it would say the following. I think I have mentioned it verbally without writing it down in earlier lectures, but is there a partition? Of irreducible representations, so G over F. I think we can allow it to be any, it doesn't even have to be quasi-split. G over F is any local group. Is there a partition of the irreducible representations of G as a disjoint union of packets with parameterized by phi? I'll say this in a moment, what it means. This would be, I think forget this. I think I'm going to stick to, just to have everything uniform, I'm going to stick to F local, but G over F quasi-split. Everything's been quasi-split since questions 2 and 3. So is there a partition of the irreducible representations of G into finite disjoint sets known now as L packets? And what are they indexed by? L homomorphisms. Phi from WF into the local L group. Well, that's a little, without specifying what this is supposed to do with trying to characterize it. We don't quite characterize it, but we're close, the way it stands today. But you put some conditions on it, and they're the nicest conditions you can sort of think of. I mean, the dual side of all of this, the parallel side of all of this Langlands program is you've got representations, and you've got L functions. And L functions are kind of a partner of representation theory. They're sort of equally important on their own. And so this is supposed to be almost characterized by L functions. L of S pi r equals L of S. We've written this down a number of times. The composition of R, phi with R, and epsilon S pi R. And then this is, in the local case, this has to be parameterized or has to be indexed by the choice of an additive character, psi f. But we would ask also that this be equal to epsilon S R composed with phi psi f. And so we would ask that this be true. Yes, question? Oh, we would ask that this be true. Well, where do you get, how do you get L functions? You need more than an automorphic, you don't need more than a irreducible representation. You also need a homomorphism of the associated L group into GLN. And so we would ask that this be true for each. Finite dimensional representation of the L group. Homomorphism from GL into some general linear group. It's only in that setting that you're able to define L functions. This is understood to be an Artinel function, a local Artinel function. And epsilon factor. No. All are. For every finite dimensional representation. It's got to be true. It's very strong. It's got to be true for every finite dimensional representation. That this almost characterizes the correspondence. We simply ask, pardon me? No, you don't. But phi is, we want to characterize, you fix phi. You fix phi. We want to characterize, we're saying that you can partition the irreducible representations into disjoint subsets, finite subsets, parameterized by phi. What are these finite subsets attached? What is the finite subset attached to a given phi? Well, it's we got to kind of characterize it some way. So this is for any phi, for any fixed phi, we would ask that for all R, these L and epsilon factors match. Now, this doesn't quite characterize it because these are automorphic L functions, local automorphic L functions and epsilon factors. And they do not have an independent characterization for all groups. We expect someday that there will be an independent characterization. This is certainly done for GLN. It's done for more general representations known as Rankin-Selberg products, for products of general linear groups. And classical groups, Piatetsky-Shapiro and Shahidi and Cogdell have gotten similar techniques to define automorphic, local automorphic, local, so these are local, I'm calling them automorphic, but I mean representation theoretic local automorphic L functions and epsilon factors, which is, I mean, if we had a characterization of them for all G and R, of course, then that would define the L packets uniquely. But this goes a long way. And actually, there is, I won't write it down, but there's an important paper by Schulze. Well, I'll just write it down. Plus collaborators, a general, it's on the web, and very long, a general characterization or proof, I would say, and that would include a classification, and I think a description of the local objects for any group, these local automorphic objects. So a general proof of this. That's great. You know, that's seems to be a breakthrough. I will say that it's not quite, we want a little bit more actually. We greedy people, we want more than just the local characterization, because we want to be able to use the trace formula. And the trace formula, well, sometimes you get to use the trace formula to prove the local characterization. That was done for classical groups. But in general, for beyond endoscopy, we're going to want to use the trace formula in ways that defy the imagination. I strongly believe that it's going to work, but it's going to dwarf other things. You know, it's not to be politically incorrect. I shouldn't use that.
General groups?
Yeah, general groups, general p-adic groups. And I haven't looked, I've only looked briefly at the paper. Oh, no, it's got to be local. No, that's, so I'm going to write down the global version in a moment. No, the local Langlands classification of this local Langlands classification. And it uses a whole theory that Schulze and people have been developing over the years. He's got funny names for them. Do you remember any of the funny names that he?
Is this Farg Schulze?
Yeah, Farg Schulze. I think. Yes. Farg Schulze. Geometrization of the local Langlands classification. And so it uses totally different theories, very sophisticated, very interesting, but I don't think, at least on the surface, it has geometric characterizations. And by when I say geometric, I mean orbital integrals, being able to write down their characters in, even if it's a complicated way, in some way in terms of orbital integrals. And that's what you would need for the trace formula. But I do think I can imagine using this in the beyond endoscopic trace formula as part of the construction. But in any case, that's the situation. I want to just be able to say now question 7. So Langlands did not say, it was just cruder what he said. He just said, is there a way you can attach representations to maps of the Weil group into the L group? The Weil group was critically important for that, but it was a more, a broader or a less precise question. And here's question 7, the last of them. This would be, suppose G over F is quasi-split. For a number field. I think he may have even had fields of positive characteristic, but for a number field. F. Hmm. I want to, okay, suppose that Langlands stated it for any L homomorphism for the L group. GL is now a global L homomorphism. And what I want to do is actually, just so it's clearer, Langlands stated it for any global L homomorphism, but I want to assume that this is a global L homomorphism that ought to govern representations in the discrete spectrum. So the condition for that is such that the centralizer in G hat, this is the condition that one puts on local or global Langlands parameters to ensure or to have them correspond to representations in the discrete spectrum in L2, either of G mod gamma, GA mod GQ, or L2 of the local field. So the condition I'm about to write down is what is supposed to characterize that in terms of the parameters, namely the centralizer in G hat of the image of phi in GL. Okay, phi is a map from this into here. This is a subgroup of this, and one would ask that the centralizer of this subgroup, centralizer of the image of this subgroup, is finite. Or maybe I should say mod, yeah, is finite. I could say modulo the center of G, but if there's an infinite center of G, there's nothing's going to occur in the discrete spectrum. And so suppose this is a local homomorphism and that pi is built out of representations pi v, local representations such that pi v. Well, if you've got a global homomorphism, I didn't write this down, but the local Weil group embeds embeds, I guess, up to conjugacy in the global Weil group. So this is just like Galois groups. This is a subgroup of this, uniquely determined up to conjugacy in the bigger group. So then, given a global phi, you can restrict it to this subgroup. So that pi v, then suppose you've got a representation pi of GA whose local components lie in these local packets. The restriction of phi to the local Weil group. Okay, so that gives you a local parameter, and you assume that conjecture 1 is proved, and so therefore you can write down the local components attached for each v to pi v. So as now a global homomorphism, and that pi is built out of representations IV from the corresponding local packets. I VV. Question, is pi automorphic? But I'm going to say that's a little bit imprecise and it's not quite true as stated. So that's why I put in this condition, the most important automorphic representations are the ones that occur in the discrete spectrum. So is pi an automorphic representation in the L2 discrete spectrum of GF over GA? And so on. So that's the last question. And a couple of comments and we're done. I'm going a bit over. I'll be with you shortly. I'm just finishing up a lecture for the other course. So so a couple of comments. So again, Langlands' assertion was considered not as precise as this, and even stated like this, it's not complete. It's not quite true. I think Langlands realized that shortly after his article. He was ahead of everybody on all of this. But so remarks. Even as written, we've written it in a very precise way. It's not quite true. But it's very nice. Langlands later conjectural theory, known as the theory of endoscopy, what it does for any such pi being a product of things in the local packets attached to the global L homomorphism. So for any pi, what it does is gives oh, I see. Come on in. Maybe I was afraid we were disturbing their conversation. Gives what it does is it gives a global multiplicity formula. Conjectural. For any pi, so a multiplicity formula for any pi this would be a multiplicity formula in global multiplicity formula. I'll write it M for the multiplicity formula for M pi phi, non-negative integer, for any pi in the global L packet. Pi phi. So the global L packet would be the restricted direct product of these finite local L packets in So we're talking about a multiplicity formula in the discrete automorphic spectrum. Which can sometimes be zero. For some pi. So strictly speaking, the conjecture is wrong because there are some pi which do not occur. Okay, one more comment and then we're done. More importantly, we have said that representations, the local representations, are classified by homomorphisms, a local Weil group, into the Galois group. This is a question about global representations and global homomorphisms of the Weil group into the L group. But this is far qualitatively, this is far differs greatly from the local one in the sense that this is correct, we believe this to be correct, but unlike in the local case, this does not give anything like all automorphic representations. It gives some of them, but by no means all of them. More important, so this is more importantly. Unlike in the local case, the union over all phi in global packets and the global packets is a sparse, a rather small subset, proper subset of automorphic representations of GAF, let's say in the discrete spectrum. They're of course important. They're for GL2, they give you automorphic forms of CM type, modular forms of CM type, but all of the other modular forms in the discrete spectrum have to be gotten elsewhere. And so this is the reason for what we have been talking about at least in the background for the last month. Hence, the need for the larger automorphic Galois group. LF, it's a fibers over the Weil group, but it's much richer, and that's what we hope will classify all of the automorphic representations. Hi, I'm sorry to keep you guys waiting.